So in last lecture, we learned about how to implement deep learning networks for semantic segmentation application and also the pose estimation application. Okay. So for the semantic segmentation, we have to rebuild the pixel-wise class. Okay. So I think this is the most naive way to implement the semantic segmentation algorithm using kind of the machine learning algorithm. So indeed, 10 years ago, when the machine learning algorithms are before the deep learning, before we use the deep learning algorithm, we implement semantic segmentation algorithm in this way. Indeed, we extract some patches around each pixel and input these individual patches to the machine learning algorithm to classify each patches. But I mean, when we use the machine learning algorithm, which is fast, this kind of thing could be achieved within a few minutes, and it was practical. But if we use the CNN algorithm, which have many parameters, then this may take a few hours, and becomes impractical. So computer vision researchers try to solve this problem and try to make an algorithm that can, input the whole input image just once, and they developed a way to output the, by feeding the inputs into the network one time. Okay, so for that, this encoder part is composed of the convolutional layers we have learned, and that layers are differentiable and they tend to reduce the dimension of the original input size. And then we calculate the feature in the middle. And then we expand their dimension again to make this kind of H by W. H means the height and W means the width of the image resolution. So we indeed upsample this feature again to the same dimensional 2D signals. And by constituting this differentiable architecture to have this dimensional output signal, we can train their parameters, theta, using the gradient descent and supplying the input and the output ground pairs. Okay, then this network will operate for semantic segmentation application. So are you guys understanding this? Okay. And the decoder size, we are using the transpose convolution. And you can observe that this transpose convolution can upsample the input signal. Actually, it enlarges the size of the responses compared to the input. And that we also observe their characteristic. And also that happens because we actually transpose the convolutional matrix, and that's why it is called as the transpose convolution and have this kind of characteristic in their operation. So anyways, this kind of semantic segmentation algorithm, you can easily implement that using the encoder-decoder architecture, and this is their code. The encoder is composed of the convolutional layers, and the decoder, they are composed of the transpose convolution operation. Okay, so this is the forward function of that. And you can use the same training code to train that encoder-decoder architecture. Okay. And then we also have to learn about the image generation part now. So previously, we have learned to generate some 2D arrays, okay, from the input image, okay. But one thing I want to additionally add here is maybe some can ask me why we have to first extract the feature first and then expand it again. Maybe some students may ask that. Then I normally answer this like this. So this feature part can have the global information about the images. So feature is encoding the holistic information about the whole images, okay? So I mean, when classifying this individual patch into the class, semantic class, you may have to know somehow the global information. So by somehow encoding, somehow compress the information from the global images into some one-dimensional vector, which is the feature vector, and from that, you can expand it to classify each individual pixels considering the holistic image information. Okay? So I mean, previous method that can make some patches like this and assign this to some ML algorithm and classify this patch into semantic class. That kind of works was prevailed in machine learning algorithms. But thing is, when these patches are given, even humans cannot maybe easily say, I mean, when only these patches are given, sometimes, for example, in this region, it is all white, okay? Maybe this is the patches from the sky, right? This region is sky. And if you extract some patch from this region, that region is rather having almost no texture and have some white pixels there. So when you see these patches only, sometimes it is hard to discriminate these patches from the sky class, right? I agree with that. So, I mean, somehow you need some contextual information to say that this patch is sky, okay? So somehow this feature have to be extracted from the global image, and we have to expand it again to somehow make our classifier to consider the global information. So, I mean, the reason why we constitute this kind of architecture is it is also trained well for the semantic segmentation algorithm. Okay. And another thing I want to say you is we generate from the input image, we could now generate this kind of 2D arrays. Okay, this is the same dimension as the original image. The next thing we might can think is we may generate some images rather than this kind of semantic segmentation map. So this map is basically having n values. They can have n values, which is maybe 0 to n minus 1. Okay, and each integer value is denoting some classes. 0 may indicate cow, 1 will indicate grass, and n minus 1 will indicate maybe sky. So anyways, this map is encoding having some discrete integer value from 0 to n minus 1, where n denotes the number of classes. This may denote number of classes. So are you guys following this? Okay. So I mean, if there are 20 classes, then this map will have the value from 0 to 19. Okay. So this is the map composed like that. But I mean, if this becomes the RGB image normally have the value from 0 to 255 and have the 3 channel, okay, to encode the RGB red, green, blue. Their intensity is denoted by these ranged floating values. So if your arrays are having 3 channels and have values from 0 to 255 for each channel, then it can become the RGB image. So we already achieved to make this kind of semantic segmentation map, which have 1 channel, but having some values from 0 to n minus 1. So if we expand this to this kind of 3-channel signals having values from 0 to 255, that can be actually the RGB image. Okay. So are you guys following this? So I mean, the same architecture could be used for this kind of application, which is, I mean, if you are further interested in this kind of method, then you can follow this, you can search for this paper published in CVPR in 2016. And actually they are having some code, Python code, okay? So you can try that. So, I mean, in image generation, what they are wanting to do is this. So given some RGB input, you can on purpose delete the center regions, okay? And can maybe this is the result where the human artist fill this blank, okay? So there's some unnatural boundary here, right? Located in these regions, there are some unnatural boundary, okay? But I mean, these two are showing the result, which is estimated from the deep learning models, okay? So maybe given this as the input, you can estimate these removed regions at the last part of the deep architecture. So if you make the deep learning architecture like that, and given this as the input and remove the patches as the output ground truth, and if you train that encoder-decoder network that looks like this, so input is the center removed RGB image, okay? And if you estimate this removed part and then compare this with the ground truth removed patch, and using the MSL loss, train this encoder-decoder architecture, then you can achieve this kind of result, okay? But one more thing is, you already learned about the L2 loss, okay, which is the MSC loss that maybe enforce this encoder-decoder architecture to estimate the patch, which is similar to, which is same as, which is close to this ground truth patches, okay? That is when achieved, we use the L2 loss. The thing is, when you use only the L2 loss, you can feel that their quality, their patch quality is not bad, but is somehow blurred, okay? So you can feel that this region is rather blurred, okay? But I mean, if you use one more additional loss function, which is called as the adversarial loss, then their quality becomes better than the left part, which is omitting that adversarial loss. Okay, so I mean, this paper is actually saying that you can achieve this using only the L2 loss, but if you use additionally the adversarial loss, that will improve your quality. Okay, that's another loss function which is important. But I mean, to be frank, this is somehow interesting loss. But nowadays we have more advanced losses compared to this adversarial loss. Okay, so I mean, for the recent research, we are not using that. But I mean, this is worth knowing. Okay, so I will explain that. So anyways, this is the architecture maybe you can compose, okay, to reconstruct some patches from these center removed images, okay. So this is the encoder-decoder architecture we just learned, okay. So in this time, but I mean, the training becomes even easier because you can in semantic segmentation case, you have to annotate this kind of ground truth with the manual effort. Okay, you have to pixel wisely generate this kind of semantic segmentation map by yourself. But I mean, in this application, given only images, you can generate their ground truth easily by just cropping that part. Okay, and then supply this as the ground truth of this network, and you make this the network's output close to this ground truth part, the ground truth centered region. Okay, so using only this amount of quality can be achieved. Okay, but I will show you what is the adversarial loss here. So adversarial loss, this is proposed in some paper called as New Rips, their conference in 2014. Okay, so I mean, this is already outdated paper. 10 years ago, it was outcomed. So now more advanced technique is replacing it. But anyways, I think this is worth knowing. What they do is you can, this might be not that intuitive. So I will show you this kind of intuitive figure first. Okay. So this is the thief, okay? And this is the police, okay? And he tried to make some fake money, okay? And he wants to deceive police to make him regard this fake money as the real money, okay? So, I mean, that's actually the laws we will use. So, I mean, actually, this thief will try to deceive this policeman, but also there are another network here. Policeman, he wants to discriminate the real money and the fake money. Okay, so I mean, you can now think that this generator and discriminator, they are independent deep architecture. So we may, we will define the generator network that can generate some new, some new data. Okay, they can generate some new, in our case, we will generate some new images. Okay, we will generate this kind of images. So this architecture becomes the SIP. Okay, so we will actually generate some fake money, and there are another network that can discriminate ours as fake and the real data as real. So there's another architecture like that. So actually, this discriminator is another network that can discriminate the data, their reality. Okay, so by competing each other, the generator and discriminator, they will compete each other. So that's why this loss is called as adversarial loss. Okay. So it somehow have the meaning of competition. So we are somehow calling this loss as the adversarial loss. So I mean, our aim is to train this generator, but discriminator is also trained during this process. So discriminator, it inputs both fake data and real data, and they somehow discriminate they tend to output 0 for generated data, and they are trained to output 1 for the real data. Okay, so that's the training, loss for the discriminator. And then what generator is doing is they are trained to deceive police or the discriminator. So this is similar to the real situation. So the thief is trying to deceive the policeman, and policemen, they want to try to improve their ability to discriminate this fake and real data. Okay, and then if thief is developing some new idea to deceive the policeman, then policemen become aware of that, and their ability is also become advanced. Okay, and then thief is also becoming advanced and advanced. So when competing each other, they become more powerful. Okay, so that can be drawn like this diagram. So this generator is the thief, okay, and this discriminator is the policeman now, okay, and the generator, they will generate some new images in our case. Anyways, we will call the generated data as the fake data. And the original image captured by the camera, we will call that as the real image. And discriminator will be trained to discriminate the fake and real data. So when fake images are inputted, it have to estimate it as 0. And when real image is inputted to the discriminator, then it have to output 1. So this is the binary cross entropy laws, actually. So we will train the discriminator as the binary classifier, and we will use the binary cross entropy laws for training the discriminator. And also, the generator will generate some data, but it is trained to deceive this discriminator. Okay, and that phenomenon is actually formulated in this formula. So I will show that. Okay. So this formula is actually having all the information about that. So discriminator, we will denote it as D, and generator, we will denote it as G, okay? And first, we will maximize this formula for discriminator, and then we will minimize this formula for G, okay? And when doing this, we will regard the generator as the constant, okay? So actually we are freezing generator while doing this, okay? And then we will freeze discriminator D while we minimize this loss function in the respect of G, okay? So first, we will do maximizing this for the discriminator, okay? So we will first do that. So, sorry. Okay, there are D here and D here, but we will regard this G as the constant now, okay? And this X is denoting the real data, okay? So P data, this is meaning the real data distribution. So this means X is following the real data distribution. So it means the X is coming from the real data, okay? And if we input X to the discriminator, then, I mean, this is the log function and d of X, okay? And D will output values from 0 to 1 because it is the binary classification algorithm. So D, when we input D, input some input to D, then it will output only the value from 0 to 1. And if it becomes 0, it indicates fake data. And if it becomes 1, we will regard it as the real data. Okay. So discriminator, they are discriminating whether the data it was real or fake. Okay. So I mean, if we input data X, which is the real data, to the input to the discriminator D, and we will maximize this term. We will first maximize this term, and you can see the log function looks like this. Okay. So the log function is looks like this. And I already said that the d of x, they are in this region, 0 to 1, okay? So in this range, when dx is from 0 to 1, if we want to maximize this log, then what would be their maximum? Maximum would be this point, okay? So in this range, what would be the log d of x's maximum? Maybe that's this point, right? And at that point, dx would go to 1, okay? Are you agree with this? So by maximizing this term, you can make d of x goes to 1, okay? It means when real data inputted d of x, d of x, their values have to go 1. Okay, so it should say the x data is real. Okay, so this is actually, I mean, by this, the d of x will output 1 for the real data. And the next thing, you will see the z is some fake. Z is this is the fake data's distribution. And z is following from, obtained from the fake distribution. And if you input z, g is some random noise actually. So from the random noise, you will, the generator will generate some fake data. So that is actually denoted like this. So G of G itself is denoting the fake data. And when fake data is inputted to D, then we have to, the D have to say it is 0. So if you draw the same graph, for this, then you can notice that the inner part have to go to 1 to maximize this term. Okay, so this term, overall term, have to be maximized regarding the D. So to maximize this, the inner term have to go 1. Okay, then it means D, G, Z, it have to go 0. Okay, so this means when you input the fake data to the discriminator, then discriminator's output have to go to 0. Okay, so are you guys following this? So this formula is actually having all the information what I told you, right? And the other part, is now, from now on, I will explain. So we maximize this formula respect to D first, and then we now minimize the same formula respect to G. And when doing this, we will regard discriminator as the constant. Okay, now this is constant because it is freeze. So this is the overall term is the constant now. So we will not care about this. The only part we have to minimize is this, okay? G is here. And we will draw another graph, maybe. Okay. Now we will draw 1 minus d gg here and log 1 minus dg of g here. Then anyways, this part is from 0 to 1. So the entire input is again become 0 to 1. So this is again from 0 to 1. And the log graph always like this. And also the range of the x-axis is always here because this is from 0 to 1, okay? And to minimize this function in this range, x range, it should go this part to minimize this, okay, regarding to this variable. So it means this variable is now going to 0. So to minimize this, the input have to go to close to 0, okay? So this happens, and it means dg of z have to go 1, okay? And this means when d is constant, which is freeze, discriminator network is now freeze, and only G will be trained, okay? So given the discriminator network, this should be 1, should go 1. So given this discriminator, GZ will make some fake data. And when this fake data is inputted to the discriminator, the fixed discriminator is becoming to say that that fake data is real, okay? So this is actually the loss function applied to generator. So the generator is now trying to deceive this fixed discriminator, and indeed, the discriminator are becoming to say that that fake data is real, okay? So are you guys following this? Okay. So because of this loss function, discriminator is now trying to discriminate the fake data and real data. They are trained using that. Actually, you can see that that's the BCE laws, okay, binary cross entropy laws. But in the generator side, it is learned to deceive the discriminator to say that the fake data, the generated data as the real data, okay? So this is the adversarial loss, okay, additionally used. So somehow, we can say this L2 loss is maybe this in this class. I mean, if you take some exam, I can let you know the answers for some questions. So that's what this L2 loss is doing. So we are teaching some answers, exact answers for the network. So for this input, generate this kind of output. We are somehow teaching the exact answers to the student, which is the network. Okay, that's what L2 loss is doing. So if we do only that thing, then somehow the knowledge is become blurred. So that's why this blurred effect is occurred. But I mean, when we use additionally the adversarial laws, then the student is now try hard to deceive another network, right? Which discriminate your answer and the ground truth, okay? So you are now getting some gradient to make some correct answer. At the same time, you try hard to deceive another man, which say your answer is wrong. Okay, so I mean for that, your final output becomes better than before. Okay, are you guys following this? Okay. Okay, so this is the final architecture, encoder-decoder architecture that we will use. So we can use L2 laws here. So to make the network's output close to the ground truth, which is removed from here. And at the same time, we have another adversarial network. Actually, this network is actually having some convolutional operation inside, and their output is actually one dimension floating value, saying the 0 or 1. If it says 0, it's fake data, and if it says 1, it means the real data. So this is actually the policeman, that discriminator network, and we will apply adversarial laws here to make this encoder-decoder try hard to deceive this network. Okay, so that's actually, the image generation. Normally, when training the image generation network, we use both adversarial laws and the L2 laws. Okay. Okay. So are you guys understand this adversarial laws? Okay. So if you are further interested in reading this, everything I explained is already contained in this paper. So you can search for this title of the paper and read more, maybe. So that's and also I explained about the pose estimation part last class. Okay, so basically it's saying we will involve some CNN-based deep learning architecture, and image is inputted, and the output is some of the floating values now. If there are 14 joint, then we have to estimate their XY value. So there will be 28 floating values. So we will actually estimate 28 dimensional some vector, okay? And we will use some MSE laws, okay? And we have to collect our ground truth by ourselves, maybe. And we can train this CNN network to output this kind of vector, which indicates the XY coordinate for the landmarks, okay? So this is what pose estimation does, okay? And after that, I said this kind of heat map representation is more easier to map for the CNN architecture. So we normally make some two-dimensional signal, okay? And we may normally make some same number of, if there are 14 joints, we make 14 heat maps. And we have to make their ground truth as well, okay? Ground truth as the heat map, represent heat map format. And for XY coordinate, we have to make some Gaussians, 2D Gaussians like this, okay? And apply the normally L2 laws to make our network to output the heat maps, okay? So actually we will implement this as the assignment 2. So I think while doing that assignment, you can maybe see the details how to implement these heat maps. Okay, we will provide you some of the skeleton code for making these heat maps and making these heat maps from the XY coordinate, and also the making XY coordinate from the heat map. So you can see the details while doing the assignment 2, maybe. Okay, and this is the example for achieving the pose estimation. So defining a lot of convolution layers, and we can get the heat map representation in the middle. Okay, it is not that different from what we learned. Okay, so we can use the same grammar of the PyTorch to make this pose estimation network. Okay. Okay, that was the thing we learned last class. Is there any questions? Okay. And another thing we now have to learn is object detection pipeline. Okay, sorry. Okay. Don't know why. Okay. So now in this class, we have to learn about the object detection pipeline. Okay. So object detection was the another very important computer vision application. So from the image, which is composed of multiple objects, we have to estimate their bounding boxes, okay, and then estimate, try to try to know their corresponding classes, okay. So that's the object detection application. So now the outputs will be look like this: the bounding boxes and also the corresponding classes and their probability. Okay. So we will learn about that. And before doing this, I have one advertisement. So the AI graduate school, they are recruiting internship students during the winter. Okay. So I mean, you already seen maybe this kind of poster maybe in the elevator, right? So if you go to this QR code, then you can see many professors document for what you will do as the intern if you come their labs, okay? And this is that QR code explaining the job description, and also you can apply by going to this link, okay? So I mean, yeah, many AI graduate professors are recruiting this internship during winter. So if you are interested in, you can anyways find this sheet in elevator or other locations and send this application to here, okay? Or also if you have questions, you can directly mail to professors that you are interested in, okay? And also, our lab is also recruiting internship students during this winter, and we are normally preparing for the hand pose estimation challenges. So our lab is normally doing the pose estimation research, especially for the hand nowadays. And we have actually received several prizes from the AI top conferences recently. So actually, one is from, this September 30th, we obtained our first prize from the ECCB 24 Hands Workshop Challenge. Okay, and also we awarded some other venues. Okay, so anyways, we are trying to develop some new algorithm for next year's challenge. Okay, so if you are interested in, please register for the winter internship. So normally the challenge will be held during the summer. So I think the winter is the best time to prepare for the next year's challenge. So if you are interested in, then you can fill in this kind of application and send it to this email address, or you can also directly mail me calling about the internship. Okay, that's one short advertisement. Okay, and so now, yeah, we are given a few minutes, but I will explain a few more about the object detection. So object detection is actually simpler than the semantic segmentation algorithm, but it's kind of more sometimes their framework is more complicated. Okay, so I explained this, in the later section. Okay, so when achieving the object detection, there could be a lot of methods. So we already learned about the sliding window scheme. So given one image, we can make this kind of small rectangle and crop the image regions inside the rectangles and input that cropped images to the deep learning algorithm to classify objects inside the region. Okay, that's the most naive way to implement the object detection algorithm. And indeed, before deep learning, many researchers are doing that to extend their image classifier into the object detection algorithm. They did this, okay? But the problem is, again, the deep learning is having very many parameters. So if you do this, it may take more than hours, okay? And also even more complicated, even more worse things in object detection algorithm is it has to consider multi-scale windows. So, this is even worse than the semantic segmentation algorithm that classify this kind of patches. Okay, the patch size for the semantic segmentation algorithm is rather even. Okay, but here for doing the object detection that can detect this kind of window that fits to the object shape, our algorithm have to have some different scaled windows. Okay, so we have to apply sliding window approach using this rectangular rectangular bounding box, or also have to apply it with this kind of rectangles having different aspect ratio. Okay, are you agree with that? So it takes a lot of time and inefficient. So the computer vision researchers are trying to solve this inefficiency problem. But before that, this is actually the algorithm proposed in 2001. Actually, 20 years ago, there was a face detection algorithm, which is called as Viola-Jones. Actually, this is the persons who proposed this algorithm, and because of that, this face detector is frequently called as the Viola-Jones face detector. And what they do is actually they apply this kind of rectangular bounding boxes around the images using this kind of sliding window approach. Okay, and then they extract the hard-like feature, which is actually the hand-engineered feature. Okay, so they they somehow get to know that this hard-like feature is efficient for discriminating the face or non-face object. So they propose to use this hard-like feature as the feature for face detector. And this is the pipeline from their paper. So they said they apply the sliding window approach, and they extract the region within the sliding window. And this is actually denoting the boosting algorithm, which is one of the classical machine learning algorithm that classify the samples into discrete classes. So boosting is one of, you can understand that this boosting is one of the algorithm that classify samples. Okay, so it will classify the input image, their extracted feature as the face or non-face. Okay, so boosting is one of classifier which is efficient to achieve the binary classification. And this is denoting the hard-like feature. Okay. So we first extract the region inside the sliding window and extract the heart-like feature on that and apply boosting algorithm to classify it to phase or non-phase. Okay? And also they applied only rectangular bounding boxes because the phase is normally inside the rectangles, squares. Okay. So that's what they implemented, and actually their algorithm was not that slow. Okay, they on CPU they can be learned within few seconds. Okay, because their boosting algorithm was very efficient. Okay, so this kind of approach, I want to show you that this sliding window approach was indeed practical for the classical machine learning algorithms, but nowadays we are using deep architecture, and that is no more practical. Okay. So the computer vision researchers are try to extend the CNN architecture, which is the image classifier, towards the object detection pipeline using this sliding window approach as well, but they feel like that it is inefficient. So instead of that, they try to reduce the number of bounding boxes. Okay, that was the first thing the computer vision researchers tried. Okay, so they try to make some bounding boxes that are likely to contain the objects. So they first try to find some image regions rather than the sliding window. They try to find image regions there that are likely to contain objects. So one of the representative algorithm is selective search algorithm. So they can find 1,000 regions in a few seconds, and that 1,000 regions may be the bounding box that are likely to contain objects. Okay, so such algorithm is called as the selective search algorithm. So given image, they try to find some bounding boxes that may contain the object. Okay, and yeah, this is their algorithm, but I think I changed the PPT, but it is not reflected here. So I will stop today's lecture here and we'll continue next Monday. Okay, thank you and see you next Monday.